Hello, in this video I am going to discuss the design of FIR filter. In this video only the implementation of the convolution will be discussed. The remaining topics will be discussed in the next video. Two signals are shown here, x of k and y of k. If x of k is the input to a system as shown here, whose impulse response is h of k, then the output y of n will be the convolution of the input signal and the impulse response as shown here. The convolution in discrete time domain in the discrete system is equivalent to the multiplication of the spectrum in frequency domain. To design a filter system, we have to find the impulse response of the system. If we know this impulse response, the values of this h of k, then we can do the convolution of the input signal and the h of k to get the filter. If we design h of k according to the low pass filter design, then these values will we will get the values of h of k, and these values will be used to then design the filter. So the this is the here I have shown the convolution sum, the form of the convolution, and then it is actually the sum of the this is the sum, and it is a sum of the two products, and one of the signal is the impulse response and the other signal is the input signal, which is rotated and then shifted. So the sum of the product of h of k and the rotated and shifted version of x of k actually gives us the output, and this is the convolution. So I will discuss in the next slides how we will do this convolution. Here I have shown the two signals. One is the impulse response of the system. This is what we have to find out to design a filter, and the other is the input signal at time t is equal to 0, and then time 1, and then time 2. This can be a signal at the input of a microcontroller, for example, and this can be implemented, these values can be implemented inside an interrupt routine to find the convolution sum. So here I've shown an example at time 5. At this one, for example, what will be the output, and this is actually the sample which will the input signal at time 5 multiplied by the first value of the h of k, and then we will multiply the previous sample with the next value of h of k, and then we will do this. Then we will multiply this value with the third value in the h of k, and then we will take this value and then multiply it with the fourth value of h of k. In this way we will get this is shown here, and in this way we will get the output at 0.5. So when we are here in time, then we can get, we have to take all the previous 4 samples, as the length of h of k is 4, including this current sample, and then multiplying it with h of k, and then we will get the output at y5 after 5 seconds, for example, if this interval is 1 second. So this is shown also here. This is the expansion of the convolution sum for y n, and varies from 0 to 5. So we can see that at time t is equal to 0 second, we will put 0 here, and then we will vary k from 0 to this value. These are the p and q are the number of samples in impulse response and in the input. So when we expand this one and put these values, you can read the values from here, and when we put these values here, we will get the output at time 0, and then at time 1, and then after 4 seconds, and then after 5 seconds, we can calculate the values of the output. So if we see what if we want to see that what is happening here, we can also see this one. Here I have removed these two terms because there are no samples at these values, so they are actually 0. So when we see here this one, the first output will be the result of the current sample multiplied by the first value of the impulse response. Then we will take the second value of the impulse response and multiply it with the previous value. Similarly, we will take the third value in the impulse response and multiply it with the value which is 2 seconds earlier than our current time. So this value will be a value which is which has occurred 3 seconds before the current value. So we can find out, we have to just take the first sample and then the previous sample which occurred 1 second before, and then the sample which occurred 2 seconds before, and then the sample which occurred 3 seconds before, and multiply it with the impulse response. So in this way we will get the current value of the output. So if we want to find out the output after 1 second, at this point of time when we apply this pulse to our system, then now at this point of time our current value is this one. So our current value will come here, and we will give the previous values here, and then we will multiply it with the consecutive values of the impulse response. So we will get the output y1 output at after 1 second. Similarly, you can see this one, we will get all the values. Every time we have to take the current value of the samples. For example, this is the current value of the sample after 2 seconds. So the current value and then the previous values of the samples. So and then we can get the current output at after 2 seconds. So in this way we can implement the convolution. Here I have again shown the convolution. Here we can see an impulse response of this system, and then I have an input signal, the same input signal, this one. So when I apply this signal to this input to this system, my output will be this impulse response, this one at the output. So when I apply this one, I will get this output. Then after 1 second I will get this output, and after 2 seconds I will get this output, after 3 seconds I will get this output. On all these 4 outputs will be due to this first sample. because this is the sample and this is its impulse response. Here is shown. So when I apply the second sample, it has a strength of 2. So my impulse response will be multiplied by 2. So I will get, after 1 second, I will get the same impulse response here, and then after 2 seconds I will get a value of 2, and then after 3 seconds I will get again 2, and after 4 seconds I will get again 2, and this output will be only due to this sample. So this output will be appearing at this point, this output will also be appearing at this point. So I have now at time t is equal to 1, we have two outputs. One is due to this sample and one is due to the second sample. So when we will apply now the third sample, again this impulse response will come at the output. It will be multiplied by 3 as shown here, and this all output will come due to the sample 2, this sample. So now I will have outputs, these 3 outputs at the output due to these three samples. So when we add all these output, we will get a net output which is shown here. You just have to add all these signals. So I have at point 0 2 signals, so my output will be I have only one signal at time 0, so my output will be 1. I have, when we see this one, this is when we see this one, this is 1 and this is 2, and there is no signal at this point, so I will have a value of 3. 2 plus 1, 3. So when we come at time 2, after 2 seconds for example, so my output will be 1, 2, and this is 3, so 3 plus 3 will be 6, so I will have an output of 6. Similarly at the next point I will also have an output of 6, and at the end we can see at point 5 I have just this output due to this x2, so I will have just a value of 3 at the output. This is what actually happens when we apply samples to our system. Our system produces an impulse response which is proportional to the value of the input signal. So when we add all these input signals, impulse responses due to individual inputs, we will get the net output. This is the way how the convolutions works. So now we can go to the next slide. This is the slide which shows how to implement the convolution with a circular buffer in a microcontroller. So I have two buffers, one this array and this array. I am storing I will store the samples, my samples in this array, and my impulse response is stored in another array. My index, we require two indices. One is the sum index and the other is the buffer index. The buffer index, for example, will be pointing to the current location where my sample will come in, and so if we get a sample, if a sample comes in, then I will write it at this position, at the buffer position, and then I will increment this buffer to the next position. So the next sample now will come at this point. So when the next sample comes, it will come at this point. So I will increase the buffer index. So now my pointer is here. The next sample will come at this point. So we can see when the next sample comes, it will be here, and I will increment this buffer index again. So when now this is my point where the next sample will come. When the next sample comes, then my buffer, it will be written here, for example here, and then my buffer will be incremented. So when because this is circular buffer, so when I increment this one, it will go to the start of the array. So now my next sample will be written here. So my buffer is pointing at this position by buffer index. So the next sample will be stored at this point. So you can see here my next sample will be or is written here, and I have increased the buffer index to this point. And similarly, now my buffer index is here. When the next samples come, I will store the next sample at this position. Here it is, the fifth sample, and I will increase this buffer to the next position. So this way we will continue storing our samples at this point and going to this point and then coming back to this point. So this will act like a circular buffer. So now when we are incrementing our this buffer index every time, we have another index which is the sum index. So sum index will be used from where we will start our multiplications. So when, for example, when the first sample comes in here, we will write this sample here. Now we will our sum index will be 1 less than the buffer index. So the sum index will be here. So we will start our multiplications and summations from here. So we have just one sample. We will multiply the current sample with the first value of the impulse response, and we will get the output. So this will be our output at time t is equal to 0 when the first samples arrives. So I have not shown the remaining terms. This I will show you later. So we don't need to multiply the other terms because they are all 0 at this point. So when the next samples comes in at this point, then this will be at this position. We have increased our buffer index, and our sum index is actually always one less than the buffer index. So we will start our multiplication from this sample. Now we have our two samples, so I will multiply the current sample with the first value of the impulse response, and then the previous sample with the next value of the impulse response. So we always multiply the current sample with the first value of the impulse response and the previous sample with the next value of the impulse response, and so on. So when we come here, we see here again that we have three samples in our buffer. So we will multiply the current sample with the first value of the impulse response and the previous sample with the next value of the impulse response, and then the last sample with the next value of the impulse response. This is also written here. So this our at time t is equal to 2 or after 2 seconds, this will be our result. Similarly, we can see here when all four samples are there in our queue, in our buffer. So this will be at this point our current sample. So we will multiply this sample with the first value of the impulse response, and then the previous sample with the second value of the impulse response, and then this second last sample with the third last value of the impulse response, and then the last value we will multiply it with the last value of the impulse response. So in this way we will implement these are the expressions which I have written here also for all these things. And here in the program, we just have to, when we write the program, we just have to increase this buffer index every time, and the sum index will be one less than this one less than this one less than the buffer index, but it will be always coming behind this buffer index. So there is another point. So when we have a buffer index at this point, and our sum index will be at this point. So when the next sample comes in, our buffer index will go from this point to this point, and sum index will come here. So the next time what will happen is this, we have to now we cannot get at this point, we can get the sum index just by subtracting -1, and then we will get the sum index. But when we are here at this point, when our buffer index is at this point and we want to find the sum index, then we have to do something like this one. So if you can see here the sum index, we will always where the buffer index is greater than 0, we will always decrease the sum index, and when if this is not the case, then we have to subtract we have to get the sum index in this way. So when the buffer index is at 0, for example at this point, then at point y is equal to 3, our sum index will be the filter length 4 minus 1 is equal to 3. So we will get our sum index at this value. This is shown in this program also. You can see here that these are all just initializations. These are all just initializations. If we here I have do if we see here there is a buffer where this will store the current value, and then I will increase the buffer index, and after if the buffer index is equal to the filter length, then we have to take it, we have to give the value of 0 to the buffer index, so that we can come at this point again. So at the start we will also take the sum index equal to the buffer index, and then we will come into the loop. So for example, when we come here, we will see that our sum index is at pointing at position 1. So if it is greater than, if sum index is greater than 0, which is at this point is 1, so we will decrement the sum index. So we will at the start our at this point we will have the buffer index will be 1 when our first sample comes in, and the sum index will also be actually pointing to 1 to this point. So 1 here at this point. So when the first sample comes in, we have increased the buffer index and have given this value to the sum index. So sum index is also pointing at this 1 value. So when we come here, we see the sum index is greater than 0, it is 1, so we will decrease the sum index. So we will come here then, and then we will start our normal impulse response. So we will get the value of first value of the impulse response, and we will get the first value from the buffer, because the sum index is at this point 0. So we will get our first value of this output. So this loop will continue, and we just use this else statement here. When our sum index is equal to 0, then when the sum index is equal to 0 at this point, at this point, if the sum index is 0, because if it is greater than 0, then we are decrementing, and if it is not equal to when it will become 0, then we will use this equation, so that we can come at this point and start our operation of the summation. So I hope it is understandable. I will discuss the filter design in the remaining video. So we will start from this slide here, how to design a how to get the impulse response which is required to design a filter. This is what we want to get to design a low pass filter or a high pass filter. When we have these values, then we will get our low pass filter or band pass filter. So thank you.